We are returning to the realm of the complex numbers once more, and this time we're going to be investigating that fascinating identity, Euler's identity, and more generally Euler's relation, and we're going to look at de Moivre's theorem. We're going to discover connections that only exist through the complex realm between trigonometry and exponential functions. So we had a little bit of a hint to this previously when we looked at the relationship between the moduli of complex numbers when they're multiplied and the arguments of complex numbers when they're multiplied. Objects that get added together when multiplication is involved may have reminded you of logarithms. In fact, the laws of logarithms and the laws of arguments appear very, very similar. That's not just a suspicious similarity. In maths, generally, if two things look the same, there is some underlying reason for that. So we're going to look more closely at why we can think of arguments not just like indices or exponents, but in a sense as indices or exponents. Before we get into that though, you probably want a bit of a refresher on some of the complex numbers manipulation that we did earlier. So here's a few questions that I'd like you to have a go at. You might need yourself a little argon diagram like mine. Start with this. Can you represent the number √2 minus √2i on an argon diagram and also write it in modulus argument form? Remember, with the cos thetas and sin thetas. For the second one, here's a number that already is in modulus argument form. I'd like you to represent that one on the same argon diagram and then convert it into rectangular form, a plus bi type thing. So z is already in rectangular form, you're turning it into mod-arg form, and w is the opposite. And finally, multiply the two numbers together, give your answer in mod-arg form, and represent that number on the argon diagram. Pause the video and work those out, and when you're ready, press play and I'll show you mine. So let's start with z. Here is z. We should have it somewhere between 1 and 2 on the real axis and somewhere between -1 and -2 on the imaginary axis. And this is what it looks like in modulus argument form. Because it is in the fourth quadrant, it has a positive real component and a negative imaginary component. We're going to have a negative argument, which is a negative acute angle. We've got minus pi by 4. It's 45 degrees clockwise from the positive real line. So we think of it as minus pi by 4 radians anti-clockwise from the positive real line. We also have a modulus of 2. If you use a bit of Pythagoras, you'll see that √2 and minus √2 combined give you a total size of 2. The length of that arrow should be 2. For w, well, we've already been given the modulus 2, so we know it's the same size as this complex number, but we've been given a different argument. This one's positive pi by 3. Still an acute angle, but this one is going to be anti-clockwise from the positive real line. So we're going to draw that one up. That's 60 degrees for those of you who are still working in old money in degrees in your head. Pi by 3 radians anti-clockwise is going to be up here. And again, you can see it's the same length as z. And if we turn it into rectangular form, it's no longer as obvious to see the size of the complex number, but we can write it relatively nicely as 1 plus √3i. Finally, you want to calculate zw, the product of the two. Now, the easiest way to do this is not from the √2 minus √2i and the 1 plus √3i version, although if you are a bit rusty and you want to check by multiplying those two in rectangular form and verifying, then by all means do so. But the quickest and simplest way is to look at the moduli, 2 and 2 in this case, and multiply them, and then look at the arguments, pi by 3 and negative pi by 4, and add them. This should be your result, somewhere that looks roughly like 4 plus I. But in reality, the exact value is 4 cos pi by 12 plus 4 sin pi by 12i, or more generally written with the 4 outside, so we can think of it as a complex number with a modulus, a size of 4, and an argument of pi by 12. So a small acute angle, pi by 12, anti-clockwise from the real line. The next thing I'm going to show you is a delightful and elegant proof of the result we're going to be investigating further today, the exponential form for complex numbers. It's not the traditional way of demonstrating this. Often when students first encounter this result, they've not done enough calculus to make sense of this. But if you've studied differential equations at A-level maths, then you'll be able to follow along. And there's not a huge amount here. In fact, it's quicker and simpler to see than the traditional approach which the textbook takes and which you can look at for yourself. The reason I prefer this one, apart from the fact that it's back of an envelope sized proof, is that it doesn't rely on any topics that you've not yet looked at. It's possible that you've not yet got to the chapter after this. It's very possible you've not got to the chapter after this yet, which involves series. So you won't have been working with the tools that the textbook proof relies on. I'd like you to work through this with me, so I'd encourage you to pause at each step and to calculate the things that I'm suggesting you calculate, and then you'll find you can generate this for yourself with a little bit of prompting. So we're going to begin with a function r cos theta plus I sine theta, but I'm going to call it y so that I can do calculus things with it. And there are two different things I want you to do with this. So on one half of the page, you're going to work with differentiation. On the other half of the page, you're going to do a little something with imaginary numbers. So separate it out, and I'd like you to do two things. The first thing is differentiate that entire thing with respect to theta. There's a reason I've called it theta. It's so that we can link it more easily at the end with the argument of a complex number. But don't let that phase you. Think of it as cos x. What would you do with cos x to differentiate? What would you do with sin x? And if you're worried about the r or the I, remember they are both just constants that happen to be there. If you can differentiate x squared, you can differentiate k times x squared. The k is just a constant. Even if you don't know its value, you know it's not going to affect the calculation that you do. I, although it may be a non-real number, is still just a constant. So that doesn't have to bother us when it comes to differentiation. The second thing I want you to do, independently of that, is to multiply your expression for y by I. So you're not doing the derivative multiplied by I, you're doing the original expression, r cos theta plus I sine theta multiplied by I. And you could just put an I in front, of course, but I'd like you to simplify it a bit and then see what you notice. Pause the video at this point, see what you come up with, and then I'll show you where we go next. All right, what we should have on the left for the derivative is r times minus sine theta plus I cos theta. Because r is a common factor, I've left it outside the brackets for the entire thing. Cos differentiates to minus sine, and sine differentiates to cos. So I've just taken each of those separate terms in turn. Now on the right, moving back across, if we have I times y, then we're multiplying the entire thing by I. But I'm not going to leave the I outside the bracket like r. I'm going to bring it in and have I times cos theta and I times sine theta. And because I times I is I squared, which is minus 1, I'll be able to simplify that a little bit more. If you look closely at those two terms, the one on the left and the one on the right, hopefully you've managed to notice something. If we simplify a little bit, put them in a more recognizable form perhaps, the real component is minus r sine theta and the imaginary component is r cos theta. And on the right, the same thing. So multiplying by I somehow gives exactly the same result as differentiating. And remember, this is for any r and any theta. It's not just a fluke for a particular complex number. Any complex number you like, the derivative of that with respect to the argument is equivalent to I multiplied by the complex number. That in itself should be a little weird, but it gets better. What we're going to do next is take these two terms, which are the same. We recognize that they're equal. And if the right-hand sides of those two equations are equal, then it must mean the left-hand sides are equal. So we can write this, dy by d theta equals iy. Now, if you think you can tell what we're going to do with this, then I would encourage you again to pause the video and have a stab at the next step. How can we break this apart, deal with it, turn it into something which does not involve derivatives? If you're not quite sure, then keep listening until the point where you think you know what you're doing, and then maybe pause and see if you can get ahead of me a little bit before you play the video again. Now, if you've got an equation that involves derivatives, we can describe that as a differential equation. Now this one is a first order differential equation because the highest derivative that appears is a first order derivative. It's got dy by d theta, but it doesn't have d2y by d theta squared or anything like that. But also this particular sort is something called a variable separable first order differential equation. Bit of a mouthful. Trust me, it gets worse when we get to second order non-homogeneous differential equations. But we start with variable separable differential equations, which means that we can separate out the variables involved. Effectively, we can pull everything involving y onto the same side of the equation along with the dy term, and we can throw everything involving theta, including constants if we like, they can go on either side, but anything involving theta must be on the other side of the equation along with the d theta term. So that's what we're going to do. Solve by separation of variables. If you think that's enough to get you started, then pause and give it a go. If not, continue watching and we'll go through exactly what that process looks like. We start with this, we divide both sides by y, and we multiply both sides by d theta effectively. Then we can integrate both sides, and on the left we end up integrating 1 over y with respect to y, so that's fine. We can integrate expressions involving y, provided we're integrating with respect to y. And on the right we're integrating I with respect to theta. Don't let this phase you. If I'd asked you to integrate 2 with respect to x, you'd say no problem, that'll give me 2x. But I is just a number, and we're integrating with respect to theta. So we're going to treat that I as any other constant. And if we integrate with respect to theta, we should get I theta. 1 over y integrates to ln y, so this is our next step. Remember, we have a constant, I theta plus c. If we ignore the constant, then we generate something, but it's not necessarily going to be the complete picture. So we include a plus c, and that takes into account the variability within both integrals. Effectively, if you had a plus a on one side and a plus b on the other side, you could subtract a from both sides, and our new constant c is equivalent to b minus a. So we've taken that into account. We've got a constant of integration, but ideally what I'd like is to have y the subject. So we've got ln y, we want y. We're going to use exponentiation. E to the power of ln y is y, and e to the power of I theta plus c will give me the right hand side. Now, you might have seen expressions like this before, hopefully you have. We can simplify still further, and generally it's considered to be a more elegant way of writing this if we can pull out the e to the I theta and the e to the c terms and separate them out of it. Because the indices are added, we can use the standard laws of indices that allow us to separate those apart. So I'm going to treat e to the power of c as equal to its own constant, capital A. And it doesn't matter what c is, c could be anything at all, and whatever it is, if you do e to the power of that number, we'll get our constant a. One thing you might notice here is that because it came from e to the c, that constant, although it can be a lot of things, cannot be negative, and it can't be 0. So bear that in mind when we get to the next step. Already we should be thinking that this is a little bit strange. We started with an expression for y which involved cos and sine. And now, with some trigonometric magic, a little bit of calculus thrown in, we've somehow managed to demonstrate that that expression involving cos and sine is equivalent to some expression involving e. And notice that theta, the argument of the original complex number, now appears as an index, as an exponent, the power within that expression. Interesting. We can go a little bit further and we substitute in our initial conditions. What this means is we've got some information because we know what y is from the top line. Y equals r times cos theta plus I sine theta. So if I want to find the value of any constants at the end, I can just go back and substitute some numbers in. So for instance, we know that y equals r when theta equals 0. We put in 0, r times cos 0 plus I sine 0. Well, cos 0 gives us 1 and sine 0 gives us 0. So the imaginary bit disappears. We're left with r times 1. So y must be equal to r. If we put that in, y equals r when theta equals 0 into our new expression here, then we can find the value of a. Once we've got a, we realize that a is just equal to r, and that gives us this. Y equals r e to the I theta. Strange, isn't it? This is what's known as the exponential form of a complex number, and it is an incredibly useful and powerful tool to use. Apart from anything else, it makes life a lot quicker and simpler for us if we're trying to write down a number in modulus argument form, because it's no longer necessary to write things involving trig, separate terms. We can combine the whole thing into essentially a single term. It's an exponential term with a coefficient at the front, and the power of the exponential term has I, the imaginary unit, combined with the argument of the complex number, and then the coefficient out front gives you the size of the complex number. Pretty clever stuff. Not only that, but now finally we can see why the behavior of the modulus and the argument makes sense. We can look at complex numbers as exponential objects, and when we multiply them or divide them, we can use the exponential laws. Now, a little word of warning, not all the exponential laws for complex numbers work exactly the way you feel like they should necessarily, but the laws for e to the a times e to the b equals e to the a plus b, for instance, and the equivalent one for division, they work just as you would expect. The complexity comes from the fact that many functions that have just a single unique value when we're dealing with real numbers may have multiple different values when it comes to complex numbers. And we'll see that already even with this particular one. We'll look in a moment at a few complex numbers generated that look like this, and we'll see how the same complex number can be represented in a few different ways. Let's start by looking at a couple of complex numbers written in this format. If z has a modulus of r1 and an argument of theta 1, and w has a modulus of r2 and an argument of theta 2, we can combine these by either multiplying, where we just put them together directly, and then using our index laws, we can see how these two nicely turn into another complex number of the same form, very quickly and easily, without having to remember any arbitrary seeming rules about multiplying moduli and adding arguments. We are just using the algebraic knowledge and understanding we already have about exponential functions to do this. And we can also divide z over w. We can do that just as well. We can divide the terms separately because it's just a product of two terms, the r term and the e to the I theta term. So r1 over r2 gives us r1 over r2. And e to the I theta 1 over e to the I theta 2, we can do a bit of subtraction of powers, and we get e to the I theta 1 minus theta 2. And again, that's exactly the behavior that we already demonstrated with cos and sine. It was a bit of a pain, to be honest, to prove that that was true for cos and for sine. We had to rely on the cos and sine multiple angle formulae with theta 1 and theta 2 like an a and a b, and cos a plus or minus b and sine a plus or minus b. It turns out we can use complex numbers and completely bypass the cos and the sine. Not only that, but we can even use complex numbers, as you're going to discover shortly, to generate for yourself the multiple angle formulae, to construct not just double angle formulae, but triple angle formulae and quadruple angle formulae, using the fact that complex numbers give us a quick and easy way into that realm. The other thing to notice about this is that the exponential function is more than what we previously would have understood it to be. If I ask you to visualize the exponential function, you'll be thinking of things like the growth of an unchecked viral infection through a population, or the growth of a population of frogs in a very large pond, the growth of rabbits through Australia, the decay perhaps of carbon-14, carbon-12, whatever it is, in a sample of organic matter. But whatever it is, you're thinking of something involving either ever-increasing growth or ever-increasing decay, depending on which way round you're going. And that's what happens when we're dealing with real inputs. But when we're dealing with imaginary inputs, we get rotation, something like this. So if we start with e to the 0, we get 1, just like you would expect. But as you increase the argument, we get all the complex numbers with a size of 1. You'll notice here, I'm sticking with a modulus of 1 to keep things simple. If the size of the complex number is 1, then changing the argument has the effect purely of rotating the complex number. It doesn't change the size of the complex number. That's what the modulus does. So we've separated out the scaling factor of the complex number and the turning component of the complex number. That's one of the reasons the modulus and argument format for a complex number is so useful. We can separate out those two components, and in fact Euler's relation, written just above, gives you essentially the same information as the exponential form, but just cancelling out the r value. We're focusing on complex numbers with a size of 1, and we can describe all of those complex numbers either as e to the power of I theta or as cos theta plus I sine theta. They are completely equivalent, they mean the same thing, and they work. You might notice though, if you're looking carefully at this, there are complex numbers like, for instance, the number -1 or the number 1, the number I or minus I. They are not generated by a single unique value for theta. Although the principal argument lies between plus and minus pi, we're allowed to have arguments of, as you can see here, 8 point something, or not just 0 and pi by 2 and pi, but we can think of it as 3 pi by 2, which is of course equivalent to minus pi by 2, but it feels like a different number the way it's written. E to the power of I times 2 pi, for instance, is completely equivalent to e to the power of I times 0. We've rotated 2 pi radians, we got back where we started. So e to the 2 pi I is equal to 1. And e to the pi I, well, that's just half a term. So that one's also a real number. It's there, minus 1. But not just those two, but any number within that circle can be described by e to the power of I times some number. And e to the I times any number will give you some complex number on that unit circle. If you're curious and you want to look at a different way of representing this particular identity, then the textbook has got an example that uses infinite series. It is really neat to see it fall out from an infinite series expansion. So if you've not yet done chapter 2, maybe come back to this after you've done chapter 2 when you've got a clearer idea of what those infinite series expansions really mean. But if you've been following along Eddie Wu's playlist on complex numbers, you may already have come across this represented in that way. He does a very good explanation of how we can build up gradually to what's termed the most beautiful identity. I alluded to it just now. E to the power of I times pi is equal to -1. But he describes the background and uses series to generate that identity, Euler's relation that we've shown up there more generally, and it's a different way of doing it completely to the calculus approach that I took in this video. So if you want to look at that, I think you'll find his videos really useful. The next thing you can try is the questions from exercise 1A in Core Pure 2. And now we're going to look in a bit more detail at some further questions. I'd like you to, again, work along with me on this one. So pause the video as and when you need to and have a go at these questions. I'd like you to start with, if e to the I theta equals cos theta plus I sine theta, in other words, Euler's relation, then see if you can explain why e to the minus I theta should give cos theta minus I sine theta. Be careful with your minus signs and look closely at what the angles are. Do a bit of substitution. And then unpause the video and continue. So, if we just substitute minus theta in place of theta in Euler's relation, then everything, of course, will work. Theta can be anything. So theta could be minus alpha if you feel uncomfortable swapping theta directly for negative theta. But if you put in a negative angle instead of theta, you'll have cos of that negative angle plus I sine of that negative angle. But then we're going to make use of that idea that we had in an earlier video involving complex numbers. We remembered that cos is an even function and sine is an odd function. So cos essentially absorbs the minus sign, whereas sine spits it out the front. We can think of cos as being a function which is symmetrical about the y-axis if you're imagining the graph. That means cos of minus pi by 6 is identical to cos of pi by 6. They're both going to give you root 3 over 2. Whereas if you try sine of minus pi by 6, it'll give you the negative of sine of pi by 6. Sine pi by 6, sine 30 is a half. sine of minus pi by 6 is minus a half. So the size of the answer is the same, but the sign is the opposite for sine. If we use those results, you can see that we can very quickly convert this expression that we've got into the form that we're looking for. Cos minus theta just becomes cos theta directly. Sine minus theta becomes minus sine theta. So the plus I sine minus theta becomes minus I sine theta. That's exactly what we needed. For the next bit, I'd like you to make use of both of those identities. See if you can combine them to demonstrate this result, that cos theta is equal to e to the I theta plus e to the minus I theta all over 2. Hopefully the format of that will help you to get a handle on exactly how to approach that. And when you've done it, I'd like you to find a similar expression for sine theta using a similar kind of technique. Pause the video, give it a go. When you're ready, come back. So what I'm going to do here for the cos theta identity, I'll start by adding the left-hand sides of the two identities and at the same time adding the right-hand sides. So e to the I theta plus e to the minus I theta. It's a good guess that this is going to help, partly because it was a show that question and that precise expression appeared in the numerator, but also because we've got a cos theta term and a cos theta term that will combine when we add them, but the I sine theta that's in this one and the minus I sine theta in this one should cancel out if we add the equations. This is essentially simultaneous equations by elimination, as you would have learned way back when. So if we do that, the I sine theta terms cancel out, the cos theta terms combine to give you two lots of cos theta, and all we need to do next is divide by 2. We've got an expression for cos theta. If you want to make the sine theta terms combine and the cos theta terms cancel out, subtract the left-hand sides and right-hand sides respectively. So I'm going to start with e to the I theta and I'm going to take away e to the minus I theta. This will give us I sine theta take away minus I sine theta, which is just 2I sine theta. We'll need to divide here by 2I rather than 2, and this is something that, if you're anything like me, you're constantly going to forget the I involved in this one. These are useful identities. You don't necessarily need to memorize them at this stage, but you may well find them helpful to pick out and highlight for yourselves. And notice that with cos theta, we get something involving exponentials on the top, and then we're dividing by 2. But with sine theta, we get something involving exponentials, then we divide by 2i. So there's something still in the cos and the sine that hint to the fact that cos is to do with horizontal and sine is to do with vertical, just like when we're resolving values on an xy coordinate grid. If we're looking at an argand diagram, we get similar kind of behavior. In fact, if you think about the angles that will make the imaginary bit cancel out, there'll be angles that make the sine theta part disappear. If you want a few extra things to try on this, I recommend substituting I theta in instead of theta to these two identities that you've got. See if you can create similar identities for sine of I theta and cos of I theta. And now we've got a way of thinking about e to the I theta. Maybe it'd be nice to think of cos I theta and sine I theta separately and see how those functions behave with purely imaginary inputs. And when you've got your results, you might want to try it out by seeing if you can find the value of cos I. And then you should be able to have a go at the first few questions of exercise 1b. Questions 1 to 5 you should be fine to try, and when you're done with those, come back and we'll go through some examples from some of the later questions in that exercise. We're going to start by looking at this one. This one is from exercise 1b, it's question 6. It's not as hard as it looks. It looks like there's a lot of horrible algebra, and if you're not careful, you might be tempted to start expanding things out and then getting stuck essentially somewhere along the way. The clue here is that it asks us to use the exponential form of a complex number. So when it talks about the exponential form, it's a massive hint that we want to try to get rid of the coses and the sines and convert things so they're written in terms of e to the power of I theta. Well, we can do that not just for cos 9 theta plus I sine 9 theta, but for every single section of that. We've effectively got 3 complex numbers all written in modulus argument form, All of them have a modulus of 1 because there's no number in front, it's just the cos and the I sine bit. And all of them have arguments which we can see related to theta. Theta is some unknown value here, but the argument of that first complex number is 9 theta. We can see that, cos of 9 theta and I sine of 9 theta. And if that's the argument, then all we need to do to put it in exponential form is put that argument in front of I in the exponential term. And we can do exactly the same thing to the rest. Cos 4 theta plus I sine 4 theta is just e to the 4 theta I. And cos 7 theta plus I sine 7 theta is e to the 7 theta I. And because we can multiply and divide exponential terms and apply our addition and subtraction laws, we get e to the 6 theta I. The last step is to demonstrate why this is equivalent to what we've got on the right hand side over here, cos 6 theta plus I sine 6 theta. And that should be pretty quick and simple as well. I'm just going to state by Euler's relation, like I did with the first one, we can work backwards as well. And that's what we're asked to show. By converting those trigonometric terms into an exponential form, we can combine them and convert back afterwards to the trigonometric form required. A couple of extra bonus questions if you'd like to try this, just to see how things combine and how the laws and the results that we've constructed and proven previously strictly within the real numbers, surprisingly enough, work just as well when we're dealing with complex numbers. Even as you discover more about the extra dimensions hiding behind the sine, the cosine, and the exponential functions, you will discover that everything that we previously believed was true is still true for real numbers and has an analogous truth in the complex plane. Here's another example I want to try. This one's question 7 from the same exercise. They've given us some clues about the complex number w, and they've asked us to find the two possibilities for w, giving your answers in exponential form. Well, if we're going to be using those clues, which seem to relate to the modulus and the argument, then it might be helpful to have z written in a modulus argument form. So I'm going to start with that. The way you calculate the mod-arg form is to calculate the modulus and calculate the argument. I've written it all out in full here, but this is a relatively quick process to follow, so it's something you should be able to do without breaking a sweat. We can see it's 1 plus I times root 3, so a quick sketch on an argon diagram is always recommended, but especially if you've got negatives involved there, it would help to make sure your argument is sensible. But if you've not, if you know that this is just going to be a nice, sensible, acute angle in the first quadrant, turning anti-clockwise from the real axis, you can just use inverse tan, and out pops the argument of 60 degrees. We can then use that and start breaking apart what's going on with the two clues we were given. I mentioned that they involve modulus and argument. The modulus bit might be more obvious to you. There's mod signs all over the place, but how do we know that there's a clue involving the argument? Well, the second thing we were given was this. The real component of z squared over w is equal to 0. And what does that really tell us? And this is kind of the geometrical reasoning part, in a sense. It's stretching it a little bit, and we'll talk about that in a moment. But to say that the real component of a complex number is 0 is equivalent to saying that the argument of that complex number is either pi by 2 or minus pi by 2. It's either a purely imaginary number with a positive number of i's or a purely imaginary number with a negative number of i's. So we've got our value of z, and now we're going to start making sense of that. Real bit is 0. The two possibilities are plus or minus pi by 2. We're thinking of numbers like 17i or minus 24i. Those are numbers with a real component of 0. And that re is used, in case you're unfamiliar with that notation, when we put im in front of a bracket like that, we're talking about the imaginary component. So the imaginary component of z we'd write as root 3. The real component of z we would write as 1, because they are the real and imaginary pieces of that number. Now, if we know what the argument should be, then here's a nice way to break apart that statement. The argument of z squared over w, we know because of the way arguments combine, that's equivalent to the argument of z plus the argument of z minus the argument of w. When we multiply complex numbers, we add the arguments. So if we're dividing complex numbers, we subtract the arguments. And in this case, we're just going to pull it apart. You might recognize shades of logarithms in here. If you have log of z squared over w, that's equal to 2 times log z minus log w. The rules are the same because arguments are logarithms. Arguments are exponentials. They are the exponents or the indices or the powers. And another word for index or power is logarithm. Now, if we can rearrange that slightly, we know the argument of z already, pi by 3. So we can simply rewrite that expression and we generate an argument for z, either pi by 6 or 7 pi by 6. Now, the only thing we've got to be a little bit careful of here is that 7 pi by 6 is outside our normal range. If we're going to be quoting this as our final result, although 7 pi by 6 is perfectly fine, if you turn 7 pi by 6 radians anti-clockwise from the positive real line, you will get to this complex number. But generally speaking, it's quoted as being something between plus and minus pi. So we're just going to subtract an appropriate multiple of 2 pi. In this case, we just take away 2 pi, and we'll get minus 5 pi by 6. All we need to do next is figure out what the modulus would be. The laws governing the modulus of a complex number are even more straightforward than the laws governing the arguments. If you multiply two complex numbers, then the moduli are multiplied, which means that z squared has a modulus which is the same as the modulus of z squared. And if we're dividing, the same thing applies. So we've got this fairly nice conversion. And if mod z squared over w is equal to mod z, as it tells us there, then we can rearrange slightly and we find that mod w has to be the same as mod z. And since we already know that mod z is 2, we know that because we calculated it earlier, we now know the size of w as well as the argument of w. And therefore, we can get our two results. Now, here's the last bit I want to talk about. The question tells us to use geometrical reasoning. And I would argue that I kind of have by saying the real component 0 suggests that we're dealing with an argument of plus or minus pi by 2. But I felt a little bit cheaty about it. It doesn't seem like the most geometrical way to think about it. So I'd also like to show you a slightly alternative version. We still end up doing similar things algebraically, but it's perhaps a clearer way to visualize what's happening, and it uses slightly different reasoning. So we're going to consider the transformations involved on the Argand diagram when we square a complex number and then divide a complex number. Let's start by looking at this one. If we begin at the point z over here, and then we multiply by z, the effect is twofold. Firstly, we are adding the argument. So if z was 60 degrees, now we've got to z squared, which is 120 degrees. But we're also scaling. We're multiplying the moduli, which means z, which had a size of 2, becomes z squared, which has a size of 4. The next step after we get to z squared is to divide by w. You can see w there. Dividing by it means turning back the way we came. W has a positive argument, which means if we divide by it, we turn clockwise. But also we're shrinking down because we're dividing the size of z squared by the size of w. And that is one of the reasons why we can see w has to be the same size as z, because we multiplied by z and then we needed to divide by w and have a number which was the same size as z. Well, if you're going to multiply by z and divide by w and not change the size of your number, we need the size of w to match the size of z. And in terms of the arguments, we need to make sure that when we turn from z squared, in order to line up with the imaginary axis, it looks like we need to turn back 30 degrees. Z was 60 degrees, z squared 120. We need to go back 30 degrees to get us to a 90-degree angle. And that's why we had w coming out with an argument of pi by 6, 30 degrees. There's an alternative version. The other one we got here when we crunched the numbers was w equals minus 5 pi by 6. You can see it represented on here. We still start from z the same way. We multiply by z, which scales things up. So we're 2 times the size, and it also rotates another 60 degrees, another pi by 3. Then we divide by a number with a negative argument, which is equivalent to multiplying by a number with a positive argument. We're going to subtract that negative argument. And subtracting a negative argument is the same as adding a positive argument. We're just increasing our anti-clockwise angle. That turns our number, in this case, well, 5 pi by 6 is 150 degrees. So we were already at 60 degrees when we were at z. We're now moving up towards z squared at 120 degrees. If we now move another 150 degrees, that gets us all the way to 270. We still need to be the same size, so the logic behind the size of w still holds, but in this case we end up at negative 2i instead of positive 2i. So we still need a size 2 at the end, but we're moving all the way to 270 degrees instead of to 90. The next thing you can try is exercise 1b, questions 8 and 9.